Hi, this is Hake. I am covering BCS Unit 6, that is Satellite Communication Link Design. For this unit, I am using a Pratt book. In, in this unit, we will see the following points. Out of these points, first point we have covered in a previous video. You refer the previous video. Today, I will cover the noise temperature and G by T ratio. System noise temperature. The noise temperature provides a method to determine the amount of thermal noise generated by devices used in receiver circuit. All of you know that in a receiver we are using electronic devices. Electronic devices generates its own temperature. That temperature is known as a thermal noise. From thermal noise, we can calculate a noise power. If noise power is greater than the signal power, that time receiver is not able to detect a actual signal. So question comes in a mind, how to determine noise power? Noise power is denoted by the letter Pn, and which is equals to K into T into Bn, where K is a Boltzmann constant whose values 1.39 into 10 to the power minus 23 joule per Kelvin, and that K value in terms of dB is equals to minus 228.6. In a noise power, T is a source temperature in a Kelvin, and Bn is nothing but a noise bandwidth in Hertz. You all are familiar with this block diagram. This is a simple receiver block diagram. I told you that every electronics device generate its temperature. That temperature act as a noise temperature. For simplicity, let us take a simple block diagram of receiver. So this is a simple block diagram of a receiver system. Here transmitter signal is coming towards a receiver side. In a receiver, antenna is receiving a signal, but that antenna creates its own temperature. And after an antenna, inside the receiver, there are many electronics devices are available. Those devices are also creating some noise. So, the final system noise temperature formula is nothing but Pn is equals to K Ts Bn into Gr. Here in previous slide we saw Pn is a noise power which is equals to K into T into Bn. But here we are considering a whole system. So whole system temperature is denoted as a TS, system noise temperature. In a receiver section, one more parameter is present, that is a antenna. An antenna has its own gain, so gain also comes in a picture of noise power. So noise power of this system is equal to K into Ts into Bn into Gr, where Pn is a noise power, K is a Boltzmann constant, Ts is a system noise temperature in Kelvin degree, Bn is a noise bandwidth, and Gr is a gain of the receiving antenna. Sometimes examiner do not give a directly system temperature. It gives a noise figure. So we should know the relation between the noise figure and the system temperature. Okay. First of all, understand what do you mean by the noise figure, and then we will understand the relation between the system noise temperature and noise figure. Noise figure is defined as the ratio of signal to noise at the input to the ratio of signal to noise at the output. Okay. And hence noise figure is denoted by NF, which is equals to S by N at the input side divided by S by N at the output side. And hence the relation between system noise temperature and noise figure is given as Ts, system noise temperature, is equals to T naught in bracket Nf minus 1, means system noise temperature is equals to room temperature in bracket noise figure minus 1. Room temperature is denoted by T naught, and which is equals to 290 Kelvin.